Hello students, welcome to the lecture number 12 on sequences and series. And the learning outcomes for this lecture are the geometric series. We will be studying about the geometric series, and also we will learn about the Cauchy's general principle of convergence. Cauchy's general principle of convergence of a series. So first of all, let's start with uh, the geometric series. So first of all, show that the geometric series a plus ar plus ar square plus ar cube plus ar raised to the power 4 plus so on. All right. Nth term would be ar n minus 1 plus so on. Show that this series number 1 converges to a over 1 minus r if the absolute value of r is less than 1. Number 2, we have to show that this series diverges if r is greater than or equal to 1. And number 3, we have to show that this series oscillates finitely if r is equal to minus 1. And number 4, we have to show that this series oscillates infinitely if if r is less than minus 1. So if you have a line here, all right, and you have this is 1, this is 0, say this is minus 1, this is 1. So you have to this is the area of modulus of r less than 1, and this is the area where r is greater than 1, and this is the area where r is less than minus 1. So you have to show that the series converges if and only if the modulus of r is strictly less than 1, otherwise it is either diverging or oscillating. And also we are given the limit of the series. The limit of the series is a over 1 minus r. So here we do the proof. So the proof of this exercise goes like this. Let Sn be, let Sn equal to a1 plus ar square be the sum of first n terms of this series, and we know that the sum of first n terms uh, is a into 1 minus r raised to the power n over 1 minus r, all right, provided r is not equal to 1. All right, let Sn be the sequence of, be the nth term of the sequence of partial sums, of the sequence of partial sums of the given geometric series. All right, then first of all we have case 1. If modulus of r is strictly less than 1, this is case 1. If modulus of r is strictly less than 1, that is r lies between minus 1 to 1, then r raised to the power n converges to 0 as n tends to infinity. Alright, and this implies that the limit of the sequence of partial sums would be the limit of a into 1 minus r raised to power n divided by 1 minus r as n tends to infinity. This would be equal to a over 1 minus r, because this limit is 0 as n tends to infinity, so this is equal to a over 1 minus r, and this implies the sequence of partial sums converges to a over n minus r, and that implies the geometric series. That means the geometric series converges to a over 1 minus r. So we have discussed the first case, that when modulus of r is less than 1, when r, the numerical value of r lies between minus 1 and 1, then in that case the series converges, because the sequence of partial sums of this series converges. A series is convergent if and only if the sequence of partial sums is convergent. So uh, this series converge, and the limit of the sequence of partial sums is called the limit of the series. So the series converges to a over 1 minus r. This was case number 1. Now we will discuss case number 2, when r is greater than or equal to 1. So this, now we will discuss case number 2, when r is greater than or equal to 1. So in two cases, when r is equal to 1 or when r is greater than 1. So next case 2, if r is equal to 1, then uh, then the geometric series then the geometric series becomes, alright, geometric series was a plus ar square plus ar raised to power n minus 1 plus so on. This was a geometric series, and the sum of first n terms was a into 1 minus r raised to power n over 1 minus r. This we have discussed already. So the geometric series becomes a plus a plus a plus a n times, infinitely, all right, infinity many terms. So in that case, uh, then the sum of first n terms would be na. In this case, the sum of first n terms would be equal to Na. This is the sum of first and sum of first n terms when r is not equal to 1. All right, earlier. But now we are considering the case when r is equal to 1. So if r is equal to 1, then the sum of first n terms would be Na, and this would imply, this implies that the limit of Sn as n tends to infinity uh, is equal to plus infinity if a is positive, and minus infinity if a is negative, and that means the sequence Sn is divergent. So the sequence of partial sums is divergent, that means the series is divergent. This implies the series is divergent, because the behavior of the series is same as the behavior of its sequence of partial sums. Since the sequence of partial sums is divergent, so the series is divergent for r equal to 1. And if r is greater than 1, if r is greater than 1, in that case, all right, in that case, r raised to power, then r raised to power n converges to infinity as n tends to infinity, and that implies the sequence of partial, the sum of first n terms, the limit of this sequence of partial sums, Alright, this is the sum of first n terms when r is not equal to 1. So when r is greater than 1, then we have the case r is not equal to 1. So in that case, the limit as n tends to infinity, as Rn approaches to infinity, so this Rn would approach to infinity, and this is equal to this limit is equal to plus infinity or minus infinity, as right, if a is positive or negative, right, depending upon a is positive or negative. This is plus infinity or minus infinity. This implies the sequence uh, of partial sums is divergent, and that implies the series is is divergent. Alright, so whether you have r equal to 1 or r greater than 1, in any case, the series is divergent. Hence, the geometric series, geometric series is divergent for r greater than or equal to 1. Alright, earlier we have proved that the series is convergent, and it converges to a over 1 minus r if the modulus of r is strictly less than 1, that means if r lies between minus 1 and 1. And also for r, alright, so it converges here, and for r 1 and greater than 1, the series is diverges. Alright, and now we will discuss the case when r is equal to minus 1 or r is less than minus 1. Two more cases when r is less than when r is equal to minus 1 and when r is less than minus 1. So case 3 is if r is equal to minus 1. Alright, if r is equal to minus 1, then the series becomes, this was the series, a plus ar square plus and so on. Then the series is a minus a plus a minus a plus a and so on. This will be the series if r is equal to minus 1, and this implies the sum of first n terms would be equal to 0 if n is even, and the sum of first n terms would be a if n is odd. Alright, so this sequence takes the value 0 and a, 0 and a. Alright, even for n even it takes value 0. Alright, and for alright, a0 a0 a0, so this is an oscillating. This implies the sequence Sn is an oscillating sequence, because the sequence Sn would be a0 a0 a0. This would be the sequence. So this is a oscillating sequence, and that implies the series is oscillating. This implies the series, the behavior of the sequence of partial sums is the behavior of the series. Then this implies the series oscillates finitely. Oscillates finitely. Alright, a sequence which is oscillating and is bounded is called oscillating finitely. So in the case when r is equal to minus 1, the series oscillates finitely, and now we have case 4 when r is less than minus 1. If r is less than minus 1, if r is less than minus 1, then minus r would be greater than 1. Alright, let minus r be called as k, and this implies k is greater than 1. Alright, now the the sum of first n terms of the series given by a into 1 minus r is to power n over 1 minus r. Alright, this is equal to uh, a over 1 minus r minus a r n over 1 minus r. All right. So and this is can be written as a over 1 minus r, minus r can be written as minus k. So this is a into minus k raised to the power n over 1 minus r, all right, which is equal to a over 1 minus r minus a into minus 1 raised to the power n into k raised to the power n over 1 minus r. Now k raised to the power n, all right, this implies k raised to power n will approach to infinity plus infinity as n tends to infinity. So this k raised to power n approaches to plus infinity as n tends to infinity, and this implies, and also you have n here, and a can be positive or negative, all right. So this implies the sequence of partial sums oscillates infinitely, and that implies the series oscillates infinitely. So we have done all the four cases when r is less than minus 1, when r is equal to minus 1, when r is equal to 1, and when r is greater than 1, and also when r lies between, case 1 was when r lies between minus 1 to 1. So in any case we have discussed that the series is convergent only when modulus of r is less than 1. That means when r lies between minus 1 to 1, then the geometric series is convergent. So a geometric series is convergent if and only if the modulus of r is less than minus 1 and the sum of the series is a over 1 minus r. Alright. So this was all about the convergence of a geometric series. Now we discuss very important. So in this series, we were able to discuss the convergence of this series because we were able to find the sum of first n terms of this series. Right? The sum of first n terms of the series was this, and we were able to find this sum, the sum of first n terms of the series. Sometimes in the series we are not able to find the sum of first n terms of this series. So if we are not able to find the sum of first n terms of a series, then it would be difficult to discuss the convergence of that series, because a series is convergent only when Sn is, the behavior of Sn is the behavior of the series. If Sn is convergent, the series converges. If Sn does not converge, the series does not converge. So for to discuss the convergence of a series, it is important to know the sum of first n terms of a series. In many series, it is very difficult to find Sn. Okay, so what to do in those cases? What if we are not able to find Sn in some series? How we will discuss their convergence? So for that, we have a general principle of convergence of a series that we will discuss next. Uh, this we will write in the form of this theorem, which is called Cauchy's general principle of convergence of a series. General principle of convergence of a series. So what is this Cauchy general principle of convergence? This principle says that a series, any series, summation n varies from 1 to infinity, is convergent if and only if, all right, if and only if for each real number epsilon positive, there exists a natural number m such that such that the absolute value of am plus 1 plus am plus 2 plus am plus 3 up to an, alright, this sum is less than epsilon for all n greater than m. This is Cauchy's general principle of convergence of a series. A series is convergent if and only if this criterion is satisfied. What is the criterion? That for each real number epsilon positive, there should exist a natural number m such that the modulus of am plus 1 plus am plus 2 plus an is less than epsilon for all n greater than m. Now we will do the proof of this theorem, and the proof of this theorem, very important principle is this. So proof goes like this: let Sn be the nth partial sum, be the sequence. Let Sn be the sequence of partial sums of this series. Let Sn be the sequence of partial sums of this series. Now we know that by definition of convergence of a series, we know that the series is convergent if and only if, alright, if and only if, let's write here, if and only if the sequence of partial sums is convergent. Okay, this is by definition of convergence, of a series, that a series is convergent if and only if its sequence of partial sums is convergent. And a sequence is convergent if and only if this sequence is a Cauchy sequence. Okay, this also we have done. A sequence is convergent if and only if it is a Cauchy sequence. And a sequence is a Cauchy sequence if and only if for each real number epsilon positive, there exists a natural number m, such that Sn minus Sm is less than epsilon for all n greater than m. This is Cauchy's criteria of the convergence of a sequence. So Sn is a Cauchy sequence if and only for each real number epsilon positive. Alright. Hence, now what is Sn in this series? Now Sn is the sum of first terms n terms of the series, and Sm is the sum of first m terms of the series. Alright, so this implies Sn minus Sm is equal to, alright, you subtract these a1 plus a2 plus a3 plus am from these terms, so what remains is am plus 1 plus am plus 2 plus an. Alright, this is Sn minus Sm. Alright, hence what we have shown, that hence the series an is convergent. This series is convergent if and only if for each real number epsilon positive, there exists a natural number m such that Sn minus Sm is less than epsilon for all n greater than or equal to m. If and only if Sn minus Sm is less than epsilon for all n greater than or equal to m. So, if and only for each real number epsilon positive, there exists a natural number m such that Sn minus Sm is this am plus 1 plus am plus 2 plus an is less than epsilon for all n greater than so we have shown, okay, we have proved this Cauchy's general principle of convergence, which says that a series an is convergent if and only for each real number epsilon positive there exists a natural number m such that the modulus of am plus 1 plus am plus 2 plus an is less than epsilon for all n greater than m. So we have proved this result, and this result is called Cauchy's general principle of convergence. So using Cauchy's general principle of convergence, we will uh, do some exercises. All right, one exercise here. So Cauchy's general principle of convergence says that a series a and n varies from 1 to infinity is convergent if and only if for each real number epsilon positive there exists a natural number there exists a natural number m such that am plus 1 plus am plus 2 plus an is less than epsilon for all n greater than n. Right? A series is convergent if and only if this exists. So now we have this example. Uh, using Cauchy's general principle of convergence show that, okay, we will show that this series summation 1 over n as n varies from 1 to infinity, this series is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on, alright, is not convergent. This series is not convergent, we will show. Alright, so how do we solve this? Solve this using this. Alright, suppose this is convergent. Suppose this is convergent. So we know that by Cauchy's principle, a series is convergent if and only for each real number epsilon positive there exists a natural number m such that this happens, such that this is less than epsilon for all n greater than n. So suppose this is convergent, all right, and let epsilon positive. Then for each epsilon positive there will exist a natural number m. So let epsilon be equal to 1 by 2. All right. Then there exists a natural number m such that uh, am plus 1 plus am plus 2, sorry, alright, am plus 2 and plus an is less than 1 by 2 for all n greater than m, okay. But if we take n equal to 2m, let's take n is equal to 2m, 2m is also greater than m, let's take m is equal to 2m, then 1 over m plus 1 plus 1 over m plus 2 plus 1 over 2m, all right, this is equal to, all right, just a minute, this would be equal to 1 over m plus 1 plus 1 over m plus 2 plus 1 over 2m, and this is equal to 1 over m plus 1 plus 1 over m plus 2 plus 1 over 2m, and this is greater than 1 over 2m plus 1 over 2m plus 1 over 2m plus 1 over 2m. All right, every time this is greater than that, and this portion is equal to m over 2m, which is equal to 1 by 2. All right, and that implies 1 over m plus 1 plus 1 over m plus 2 plus 1 over n, this modulus is greater than 1 by 2. All right, so we have got a contradiction. Why? Because here we are saying that this number is less than 1 by 2 for all n greater than m. This number is greater than 1, less than minus 1 by 2 for all n greater than m. But if you take n equal to 2m, then this number has come out to be greater than 1 by 2. So we have got a contradiction. So this contradiction arises because we suppose that this series is convergent. So this series is not convergent. All right, hence this series is not convergent. So the given series is not convergent. All right, this was an example here, and now we have another important result that we would like to discuss, and that result is this. We have this theorem, and this is a very important theorem. This says that if a series is convergent, if this series is convergent, then the limit of its nth term would be 0. Then the limit of its nth term would be 0. All right. So we have to prove this, and the proof goes like this. Suppose it is convergent, is convergent. All right, suppose it is convergent means it converges to some real number. All right, and let Sn be the sequence of partial sums, be the sequence of partial sums of this series. All right, this implies the limit of Sn is equal to a. Now what is an? An is equal to Sn plus 1 minus Sn. All right, because n plus 1 is a1 plus a2 plus a3 plus an plus 1. This is Sn plus 1, and minus this is a1 plus a2 plus a3 plus a a sorry, this would be this is Sn minus Sn minus 1. All right. So this implies the limit of an as n tends to infinity is equal to the limit of Sn as n tends to infinity minus the limit of Sn minus 1 as n tends to infinity. And the limit of Sn, since the sequence of partial sums converges to a, so this implies this limit is a and this limit is also a, which is 0. And that implies the limit of an as n tends to infinity is 0. Alright. So we have proved this theorem completely, that if a series is convergent, then its nth term, the limit of its nth term would be 0. So straight away we can say that if a series is not convergent, if the limit of the nth term is not 0, then the series will not be convergent. All right. For example, all right. For example, Alright, this series, uh, say let's write summation, uh, 3n minus 1 over 2n plus 1 as n varies from 1 to infinity is not convergent because the limit of its nth term as n tends to infinity. If you find this limit, this would be 3 by 2 and this is not 0. This limit is 3 by 2 is not 0. Alright, so we have done that. If a series is convergent, then the limit of nth term must be 0. If a series is convergent, then the limit of the nth term is must be 0. Now in this case, in this series, the limit of the nth term is 3 by 2, which is not 0. So this series is not convergent. So this result is helpful to find if a series is convergent or not. That is the end of this, and we will continue in the next lecture. Thank you.